Hello there. So we're looking at a problem here where you have to find the x and y components of a force that's in the situation. And this is just some sort of 25-kilogram object being pulled on by a rope. The rope is at an angle of 40 degrees with the horizontal, and the tension in the rope is 100 newtons. And we're not going to have any friction in this problem. So let's start where we always start, with a free body diagram. We're going to have the force of gravity, and of course that's equal to m times g, and in this case that's 25 times 9.8, and that's going to give us 245 newtons. And then we always want to think about what is touching the object. There's a contact point with the ground. There's a contact point with the rope. Anywhere there's a contact point, there's going to be a force with the ground. The ground's going to push up, and we call that normal force. No friction in this problem. With the rope's going to pull at the same angle that the rope is oriented, so 100 newtons. And let me just draw an x and y axis here so that I can measure that angle from the horizontal, 40 degrees. And that's it. Those are all the forces that are acting on this object. By the way, didn't tell you what we're trying to find here. Let's see if we can figure out its acceleration, and let's see if we can figure out what the normal force is equal to. Okay, back to what we would do next. Now, when you have a problem where one of the forces is at an angle, the next step is always going to be find the x and y components of any forces at an angle. So I'm going to start at the tip of this tension arrow. I'm going to drop a perpendicular down to the x-axis so I can accurately draw the x component of that tension force and the y component of that tension force. And then to calculate those things, I'm going to have to use sines and cosines. So the x component is adjacent to the 40-degree angle, and so I would use cosine. Cosine of 40 is adjacent over hypotenuse, which is 100. And so that's going to be 100 times the cosine of 40. And according to my calculations, that is 76.6 newtons. Over here, we're going to use sine. Sine of 40 is equal to opposite over 100. So the opposite is equal to 100 times the sine of 40. And I come up with 64.3 newtons for that component. Okay, so once you have all of your components, you can start to write your Newton's second law equations. Let's do one for the x direction. So I'm just going to include forces in the x direction here. And that's pretty easy, because in this picture, we got nothing pointing to the left. The only thing pointing to the right is this x component, which is equal to 76.6. So right off the bat, we can figure out what the acceleration is, and it turns out to be 3.064, I believe, meters per second squared. And we've answered that question. Now, if we do the Newton's second law equation for the y direction, and we put in those y forces, we do have the normal force, so that's positive Fn. We also, in addition to that, have the upward component of tension, which we figured out was 64.3. And then, of course, we have the downward force of gravity, which is 245 newtons. Now, the other additional piece of information here is that the acceleration in the y direction is equal to 0. And that's because, and this is a little bit of an assumption that I'll talk about in a moment, we're assuming that the rope is not pulling so hard to lift this up off the ground, that it's just staying on the ground. Sure, it's moving sideways, but it's not moving up or down. If it's not moving up and down, then its y acceleration is 0. And I always tell students 99% of the time, if you've oriented your axes correctly, you will have one of your two directions have an acceleration of 0. Always think about that. Oh, which direction has the acceleration of 0? Is it x or is it y? It's a very, very rare situation where they both have acceleration. So anyway, we can do the algebra here, and we find out that the normal force is equal to 245 minus 64.3, which is 180.7 newtons. And logically, it makes sense that the normal force is not equal to the weight, it's less than the weight, because the rope is actually helping to support the mass. Now, here is it. Let's go back to that other question. How do we know it's not accelerating up off the ground? So let's see if we can answer that. If suddenly we start increasing this 100 Newton force, making it bigger and bigger and bigger and bigger, how big would it have to be to just be at the point where this thing is about to lift up off the ground? So to solve that problem, what I want to do is recalculate the x and y components of that force. So now it's not 100 anymore. Now it's an unknown. It's just F. This is still 40 degrees. It still has x and y components that look like this, but now the x component is going to be the cosine of 40 times adjacent over F, not over 100. So we have an expression, F times the cosine of 40 is the adjacent side. And likewise, sine of 40 equals opposite over, again, F, it's unknown. So F times the sine of 40 equals the opposite side. So if we plug this now into our x and y equations, let's see what happens. So in the x direction, we're going to have F sine 40 as our only x direction force. Mass is, of course, 25. We have too many unknowns here. We don't know the x acceleration. It's not the same as it was previously because now you're pulling harder. So it's not 3.064 anymore. And it's not 0. So we're kind of stuck here. Let's go with the y direction. And in the y direction, we still have the normal force. We now have this expression, F times the sine of 40, and we still have negative 245. And at first glance, it looks like we're stuck again because we have tons and tons of unknowns here. So here's where we have to go back and think about what are our conditions here. We're pulling so hard that it's just about to lift off the ground. Well, guess what? If it lifts off the ground, if it doesn't touch the ground anymore, there's no normal force. So that's really the mathematical way of expressing that it has lifted off the ground by saying, hey, the normal force has gotten so small that now the normal force is 0. It's not touching the ground anymore. The other thing we're going to do here is, since we're just barely at the point where this is about to happen, we're going to say that it's still just barely touching the ground when the normal force is just barely 0. So the acceleration in the y direction is 0. And that might seem like cheating a little bit, but this really is that boundary condition. What is the last moment that it's kind of still touching the ground, but kind of about to lose contact with the ground? And so that's how we can justify saying that both of those things are 0. So then this equation just becomes F that we're looking for is equal to 245 divided by the sine of 40. And that gives us an answer of 381.15 newtons. So if you pull that hard, then 100% of the support for the object is being provided by the y component of the tension. Normal force isn't doing any work anymore. And if you pull with any more force than that, it's going to lift up off the ground. If we want to, now we could figure out what its acceleration would be at that point. Now that we know that this force is 381.15, multiplied by the sine of 40, divided by 25, we come up with a pretty big acceleration of 11.68 meters per second squared. All right, hope that helps you with this type of problem. See you next time.